Hi, everybody, and welcome to a brand new semester in our ESACS geometry course. My name is Mr. Lamping, and we're going to take a look at Unit G as we start things off here. We're going to look at polygons and parallelograms and quadrilaterals. It will include rhombuses in this. We'll include trapezoids in this. We will include kites. And who knows what else might pop up in this particular unit. But it is going to be talking about the properties of polygons and mostly quadrilaterals. So first of all, let's take a look at something called the polygon angle sum theorem. If you were to take a polygon and add all the angles together, well, depending on the polygon, that answer would be a different number. But for every quadrilateral, it would be the same. Every pentagon, it would be the same. Every hexagon, it would be the same. So the sum of the interior angles of an n-gon is n minus 2 times 180. And when we get to an example, I'll show you why that is. So that's a formula that you're going to probably want to have prominently displayed in your notes somewhere. So I would make sure you have that so you can easily find that. N minus 2, and n is the number of sides, times 180. A regular polygon is a special type of polygons. First of all, an equilateral polygon, all of the sides are congruent. This is not regular, but it's equilateral. Equiangular is one in which all the angles are congruent. So if you have both of these properties, you have what's called a regular polygon. It's usually the polygon you think of when you think of a triangle. You usually end up drawing an equilateral triangle. If you are thinking of a regular quadrilateral, you a lot of times draw a square. A pentagon looks like the pentagon from Washington, D.C. A hexagon looks like this, usually when you think of it. Those are the regular versions of those. But see, this is a hexagon over here. It just doesn't look like it might be. This is also a hexagon. So anyway, when we get to that, regular polygons, every angle is the same measure. So if you want to find the measure of one interior angle of a regular polygon, you simply take the formula from earlier and divide it by the number of sides or number of angles that you have. And then the last thing we have is the exterior angles. Now that's a whole different ball game right there. The sum of the exterior angles of an n-gon is 360 degrees. Doesn't matter how many sides it has. You just add up every single exterior angle, it's always going to add up to 360 degrees, whether it's regular or not. Doesn't make any difference. So that's kind of an easy one to think about. So let's take a look at a couple of examples. And so here's what I'm talking about, the sum of the interior angles of a heptagon. Well, you've got to know what a heptagon is. Heptagon has 7 sides. So if you think about that, and I'm just going to draw a very rough heptagon. 1, 2, 3, 4, 5, 6, 7. So what would be the sum of all 7 angles? Well, we could use the formula, but in order to understand the formula, why don't I take and I start with this point. If I just simply drew all the diagonals, I would create 1, 2, 3, 4, 5 triangles. Each triangle, the sum of the angles is 180 degrees. So it makes sense that since I have 2 less triangles than the number of sides, that this formula would definitely tell me the sum of those angles. So yeah, 7 minus 2 times 180 would be 5 times 180. I'm just going to grab my calculator here, and we're going to do 5 times 180. And that's going to give me 900 degrees. So 900 degrees would be the sum of every heptagon, not just this one, but every heptagon. All right, a housefly has eyes that consist of about 4,000 facets in the shape of regular hexagons. What's the measure of each interior angle of each facet? So basically, we're looking at one hexagon, regular hexagon, and we want to know what's the measure of that one interior angle. So you got to assume that that's regular. So I want one of them. So first of all, it's got 6 sides. I'll come over here and I'll plug 6 in for n in both cases. 6 minus 2 times 180 divided by 6. That's going to be 4 times 180 divided by 6. Again, grabbing the calculator, we're going to get 4 times 180, which is 720. We divide that by 6. we get 120 degrees. And so we get 120 degrees. And if you notice, they're all obtuse angles, so that makes sense that it's 120 degrees. Okay, this is a pentagon, and I can tell just by counting the angles, 1, 2, 3, 4, 5, or the sides, there'll be 5 of them. Question is, what's the measure of angle Y? So basically, I need to know the sum of the angles, so I'm going to take 5 minus 2 times 180. That would be 3 times 180, and 3 times 180 is 540. So I need to add up all of these angles, and they have to add up to 540 degrees. So I'm going to basically write 540 equals, and I'll start here. 110 plus, well, that's 90, plus 120, plus 150, plus y. And I have to solve that for y, and that'll be my answer. So if I add up all those numbers, 110 plus 90 plus 120 plus 150 is 470. So 540 equals 470 plus y. We subtract 540, and I get, this says negative, but that's because I subtracted in the wrong order, so 70 degrees. So y would equal 70 degrees. Simple as that. And the last one says, what is the measure of angle 1 in this regular octagon? So they're all the same, but remember, these are exterior angles. So the exterior angles are simply, the sum of all of them is 360 degrees, and since there are 8 angles, we just divide that by 8, and we get whatever 360 divided by 8 is. It happens to be 45. So 45 degrees would be the measure of angle 1, actually be the measure of any of those angles, 45 degrees. And there's your notes, and there's your examples for section G1 in our brand new semester, in our brand new unit.